Null and absence. Not all data is always present. Sometimes a value is missing. A user might not have a phone number. A search might find nothing. A file might not exist. How do we represent no value? This is the problem of null and absence. It is simple, but causes countless bugs. Today we understand it deeply. Consider a user profile. Name is required. Email is required, but phone number, optional. Some users have it, some do not. What do we put for the phone number when there is none? We could use an empty string, but empty string is a valid value. It is not the same as no phone number provided. We could use a special value like n/a, but that is just a string. The code might accidentally treat it as a real phone number. We need a way to say, there is no value here, not an empty value, not a placeholder, truly absent. This is what null represents. Null is a special value. That means no value or absence of value. It is not zero. Zero is a number. Null is not a number at all. It is not an empty string. An empty string is a string with no characters. Null is not a string at all. It is not false. False is a Boolean value. Null is not a Boolean. Null is the absence of any value. It represents nothing. When a variable is null, it contains no data. It does not point to anything. It is empty in a fundamental way. Null exists in most programming languages. The concept is universal, even if the name differs. Null is dangerous. If you have a value and try to use it, things work. If you have null and try to use it as if it were a value, things crash. This is the null pointer exception, the null reference error, the billion-dollar mistake as its inventor called it. You expect a user object, you call user.name, but user is null. There is no user, there is no name. The program crashes. This happens because null can appear where you expect real values. The type says user, but the value might be null. The type lies. Null turns what should be type errors into runtime crashes. The compiler says this is a user, but at runtime it is nothing. The danger comes from null being implicit. In many languages, any reference can be null. You get a user, but it might be null. You get a string, but it might be null. Every value is secretly value or null. This is implicit absence. Absence is always possible, but rarely acknowledged. Better languages make absence explicit. A type is either definitely has a value or might be absent. You must declare which. With explicit absence, the type tells the truth. If it says user, it is definitely a user. If it says user or null, you know to check. This makes null handling a conscious choice, not an afterthought. How do you work with values that might be null? First, check before using. If the value might be null, verify it is not null before accessing it. Second, provide defaults. If null, use a fallback value. Third, fail early. If null is unexpected, throw an error immediately rather than letting it propagate. First, avoid null when possible. Use empty collections instead of null collections. Use optional types that force handling. The key is being deliberate. Know where null can occur. Handle it explicitly. Many modern languages have optional types. An optional type explicitly says, this might be absent. Instead of string that might secretly be null, you have optional of string. The type itself declares the possibility of absence. When you have an optional, you cannot use it directly. You must first check if a value is present. The type system enforces this. Optional types turn runtime null errors into compile time type errors. The compiler catches missing null checks. This is safer. You cannot forget to handle absence. The type reminds you. When designing data, think about which fields can be absent. Required fields, always present. Use non-nullable types. Optional fields might be absent. Use nullable or optional types. Be deliberate. If something is always required, do not allow null. This prevents accidental nulls. If something is optional, document why. When would it be absent? What should code do in that case? Consider empty values versus null. An empty list is different from no list. An empty string is different from no string. Choose the right representation. Good data modeling makes null explicit and rare. One null can lead to many null checks. If user might be null, and user.address might be null, and address.city might be null, you need checks at every step. User .address .address .city .uppercase. This is null propagation. If any step is null, the whole expression is null. You do not crash, you get null. This is convenient, but can hide problems. If something should never be null but is, the null propagates silently. You might not notice until much later. Balance convenience with clarity. Sometimes failing fast on unexpected null is better than propagating. Tony Hoare, who invented null references, called it his billion-dollar mistake. Not because null is always wrong, but because null being implicit everywhere causes enormous damage. Countless bugs, countless crashes, countless hours debugging. The lesson: absence is a special condition. It deserves explicit handling. Hiding it in every type causes more harm than good. Modern language design learns from this. Explicit optionals, non-nullable types by default, tools that help you handle absence correctly, understand null's history, respect its danger, handle it explicitly. Let us summarize. Null represents the absence of a value. It is not zero, not empty, not false. It is nothing. Null is dangerous because using null as a value crashes the program. Implicit null. A value might be null, hides the problem. Explicit null. Any value might be null, hides the problem. Explicit optional types reveal it. Handle null safely. Check before use. Provide default. Optional types make absence part of the type, forcing explicit handling. And data models distinguish required and optional fields clearly. Null propagation can be convenient but may hide problems. Respect null, it represents a real condition. Absence but requires careful handling.